Okay, let's keep on talking about springs now. We've talked about energy in the previous video. Now we're talking about springs. Again, this is going to be more of an introductory lecture video. Not really solving any complex problems here, but we are getting the equations that we'll be using. So, springs, as a reminder, a spring is pretty much a coil of wire. It doesn't have to be just a coil, though. Anything could act like a spring. Could be like a rubber band. It could be, let's see, like the gravitational pull of a planet. What goes up must come down. It's kind of acting like a spring, right? Um, but the force isn't necessarily changing as much as a spring would. But anyway, so talk about a spring. This spring, as you stretch the spring, as you compress the spring is going to push or pull back the other way. And what we've learned before in forces is that the force of a spring is equal to negative k delta x. And the reason why we have a negative is because if you were looking at the force of a spring, if we were to compress it a certain distance, negative x, the spring would push back in the positive direction. And if we were to pull the spring a distance of positive x, the spring would pull back in the negative direction. So that's why we have that negative there. So, how did we get this? Now, if you remember back to the spring lab, you guys were having to find the value of k, and the k is the spring constant. Its units are newtons per meter. And you did the lab, and you guys were getting all frustrated because we're getting k values, and they're all different. What the heck's going on? And you sat there and you argued back and forth because people were doing it differently, and everybody was getting different things. Well, the reason why everybody was getting different things, it's not that you were doing it wrong. It's just that you guys were taking individual plots of data to find k. Because each and every time you would take force, whatever force you applied to it, divided by however far it stretched, and that for you would be equal to your k. Well, imagine what's going on there. If you, for every whatever f you have, you measure some x, that's going to give you some k. And so, like, if we had a graph of force, as units of newtons, and we got some change of position x here, and that's going to be in units of meters. Well, if we had, let's say, this one data point, and you found k, you pretty much found the slope of whatever line that is. And whatever line that data point goes to from 0, you found that slope. And if if you did not as much of a change of x, and you went over here and you did f over x, you pretty much found that slope, which is different from this slope. And so you kept on taking data, and you kept on making these one calculation moves, and you kept on getting all these different slopes. Well, duh. Yeah, you're going to get these different slopes, human error and all that stuff. Some people were getting the same slopes, and that's fine. But really, most groups were just getting these different slopes. And so you took all this data, and it came out to where it's like, it's kind of scatter plotted. So each one of these has its individual slopes. Well, what do you do with that? Here are all your plots. If you took a million more dots, you'd eventually get something that would represent a straight line. But we're going to use what's called a line of best fit, and that's going to pretty much go through all of them. Okay? So then, if you found this line and you had, you knew numbers on these axes, you can find the slope of this, which would be a change in f over a change in x. It's a rise over run, and that should give you a k value. Okay? And it won't come out to be negative, but you can just apply that negative there. The k value is a positive number. It's just a magnitude. It's how much. All right? And that's how you do it. Well, think back, and let's talk about other graphs that we've worked with, and we'll just quickly do this. What about a velocity graph per time? What happens there? Meters per second. Let's do seconds. Okay, what happens with a velocity graph? What if my velocity graph looked like this? Okay, what does that tell you about velocity? Well, the slope of that line tells you that the velocity is increasing per second, right? And it's increasing at a constant rate. Well, that means we have a constant acceleration. If my velocity graph looked like, let's say it looked like this. Oh, here's my green. It's not working out too well. There it is. So let's say my velocity graph looked like that. Well, what's happening here? My velocity is increasing at a constant rate, and then it doesn't come to a stop, but it just stops increasing. So I'm still moving. And then here we start to slow down a little bit. And then we start to speed up a little bit. So my acceleration is changing here, right? So the slope of the velocity line tells you your acceleration. Now, there's something else that we can get from the velocity line, and that's the area underneath this line. Okay, let's use that black line for now. So the area underneath that line tells you how far it went. Velocity times time. That gives you how far you went. If your velocity was, let me use a different color. If your velocity was a constant, okay, then if we took velocity and we multiplied by a change in time, that should give us a change in position. And you guys should be familiar with this by now. Well, let's go back and apply it to this spring graph. So the slope of my spring graph gave me a change of f over a change of x, and that is going to be k. Okay? So looking at this, what would the area of this graph give me? And so what's the area of this graph? What is this shape? It's a triangle. The area of a triangle is going to be 1/2 base times height. And so for this graph, we have 1/2 base, which is a change of x, times the height, which is going to be a change of f. Okay? Well, what does that give you? Let's take a look at the units. What are the units of x? The units of x are meters. Okay? What's f? What are the units of f? The units of f are newtons. We have newtons times meters. In the previous video, we learned that newtons times meters is equivalent to joules. That's equivalent to work. Okay? Or energy. So in this case, if it's a spring and we're pulling on it or pushing on it, then we're building up this potential energy, this potential to move something faster later on. And so the area of this graph is going to be the potential energy stored in that spring based upon this. And we're going to make this look a little bit nicer, give you the standard format. We know that F is equal to Kx. And so if I replace this and I say, hey, 1/2 change of x is equal times F, which is going to be Kx, that's going to give me 1/2 Kx squared. Okay? And so that's going to be our new equation for a spring. The energy of a spring, anyways. The potential energy of a spring equals 1/2 Kx squared. Okay? And the units of this, since it's energy, is joules. All right? And to do a quick problem over how you would use that, well, let's say that we have a... do we want to shoot something, or do we want to absorb some energy? I don't know. Oh, let's say we want to shoot something. So we have a dart gun, spring-loaded Nerf gun. So in this thing we have a spring, and we've got this dart, and let's see, it's got a nice little tip here, and it's a soft dart. So we've got this dart in here, and we've actually compressed the spring a little bit. So the spring's actually not that long originally. It was about out to here, and let's use dotted lines here. So we got this dart, and let's say we've actually compressed it a distance of 4 centimeters, so 0.04 meters. Okay, and this dart, it's going to have a mass of like 10 grams. Let's make it 10 grams. So 0.01 kilograms is the mass of the dart. And the spring has a spring constant. And somebody's going to yell out a number. They're going to say, oh, it has a spring constant of 150, because you guys like to yell out weird numbers. So let's find out. If we let this thing fire, how fast is this gun going to, or how fast is this dart going to be moving out of the gun? And so what we're going to do is we're going to look at the energy involved. Well, how much energy, or what kind of energy does it have right now before we fire it? This spring is pent up with potential energy, and we'll just draw a little spring there to denote that that's the kind we're going to talk about. And when this dart is fired, the spring is going to extend, it's going to transfer its potential energy, and it's going to turn it into kinetic energy. And due to the law of conservation of energy, if we ignore some friction, we always say we ignore friction. Friction's actually kind of hard to account for in most situations. Sometimes it'll be easy. Most times in real life, it's kind of hard. But my energy in the beginning is spring potential energy, or 1/2 k x squared. And finally, it's going to be 1/2 m v squared, or kinetic energy. And we're looking around, things might cancel out. The 1/2s are on both sides, so we can cancel that out. And we're left with k x squared equals m v squared. And if we want that v, we're going to go ahead and move the mass over. And we want the v, we want to square root it, so there we go. And so for this problem, we have a k value of 150. We've got an x value of 0.04 squared divided by the mass, which is 0.01, and we're going to square root it. And so take my calculator, 150 times 0.04 squared divided by 0.01, and then we square root it, and that's equal to 4.899. We're talking about velocity, so meters per second. All of our units should work out. Okay, so that's just utilizing a spring, showing you where that equation comes from. And now we'll do some examples.